Okay, so first section we're going to take a look at is 1.1. Okay, it's on functions and graphs. Okay, a lot of different things in this section are going to be review. So we're going to talk about like what an equation is, the distributive property, commutative, associative, a few names of properties, and then graphing with like open circle, closed circle. So this section is kind of a mix of review topics. Okay. In fact, most of chapter 1 I think is review. So we'll go through that kind of quick. But when we get into like chapters 2, 3, we'll definitely slow down. All right, so the first thing we're going to take a look at is this number chart. Okay, so I'm not going to write down every single definition, but what I'm going to do is just kind of explain each number set to you, starting with the simplest numbers, working our way out to more complicated. So simplest kind of numbers you can have are counting numbers. Okay. Brendan, when you start counting, what number do you start with? 1. 1. And then the next number? 2. 2. You don't start with 0. There's no negatives. And notice he didn't say 1.5. Okay, when you're counting, it's just 1, 2, 3, 4, 5, 6, 7. You just use positive numbers, no fractions, no decimals. The reason why we can't stick with just counting numbers, or one reason, is because when we start doing arithmetic, we can run into problems. For example, Eric, can you give me a counting number? 3. 3. And then I'm going to use the operation subtraction and put 3 again. So I have a counting number minus a counting number. Now, we know what 3 minus 3 is, right? It's 0. But is 0 a counting number? No. So if all you understand, like pretend all you believe in is counting numbers, you would have to say something like this is undefined. You can't do it because there's no answer. There's no number that we have that would represent 0 till we go to the next number system or next number set, whole numbers. Only difference between whole numbers and counting numbers is whole numbers include 0. Now you can do something like this because we basically invented a number, 0, that means nothing. It means when you subtract the same thing from itself. Right? Now, if you have whole numbers, adding would work fine. If you add 2 whole numbers together, you'll always get an answer that's a whole number. How about subtracting though? Can anybody give me an example of a whole number minus another whole number, but the answer is not a whole number? Yeah, Zach?
3 minus 4.
Yeah, that's a problem. So if all you believe and all you understand is whole numbers, you can't do a problem like that. Right? If you put that on, like a second grade, math textbook, 3 minus 4, and a second grader looked at it, they'd be like, you can't do that because they don't understand the concept of negative. All right? So that's the next number system. So we invent all these numbers, and now we call them integers, so that we can represent having even less than nothing. So not only is it nothing, it's even less than nothing. Right? It's negative. And that's where integers come in. Now, if you add, subtract, multiply, you're fine. If you give me an integer plus an integer, I'll always get an integer for an answer. Same thing with subtraction, same thing with multiplication. But what could happen with division, where you give me an integer, you give me another integer, but the answer is not an integer? You want to give me that?
It would be a rational number.
All right, can you give me an example?
Like 1 over 2.
1 over 2. Right. If integers are the highest, most advanced type of number you understand, you can do positives, negatives, and 0. You can't do this. And even practically, like if you want to take one object and you want me to give this one object to 2 people, that's what division means. Take one thing and split it into 2 parts, right? I can't do that, right? Unless I'm going to take this and break it into pieces or fractions. And that's the next number set, okay, rationals. So we keep inventing new kinds of numbers so that we can solve problems like this. It's a very simple problem, 1 divided by 2. But if you don't have decimals invented, you can't do it. So they invented the decimal point, and now you can do fractions or parts of things. And rationals, I do have the definition for that one. I thought it, nope, never mind. So a rational number is basically an integer in the top, integer in the bottom. This is not really a rational number. 1.5 over 3.7. If you're going to write something as a fraction, I would just write this as 15 over 37. That's really how you should write that. So integer in the top, integer in the bottom, rational number. For most everyday purposes, that's about as advanced of a number as somebody needs. Okay? Maybe you're cooking and you need 2/3 of a cup of flour. It's not 0 cups, it's not 1 cup, it's in the middle. It's a fraction of a cup, 2/3. If you buy something at the store, maybe it costs $12.99. It doesn't cost $12, it doesn't cost $13. It costs $12 and then 99 hundredths of the next dollar. So it's a fraction, it's a decimal amount. Going beyond rationals, now we start to get into numbers that are used less often. I mean, they're still used. Like we use them, I'm sure I'll be able to ask you a question. You'll be able to tell me where we use them in a second. But an example of an irrational number is a number you cannot write as a fraction. Can somebody give me a number that you can't write as a fraction? And this number is, well, if you give me the one I'm thinking of, it's used all over the place, especially in geometry. Yep. Pi. Pi is an irrational number. And some people say, well, isn't 22 divided by 7? Isn't that the fraction for pi? Not really. And you get the 3.14, but it's 3.14159. So after 3.14, 22 over 7 isn't that accurate. So pi we can't write as a fraction. Also, square roots. I mean, square root of 4 you can do. That's a nice answer. Square root of 9. I'm talking about square roots like square root of 2, 5, 6, 7. These are all numbers that when you type them in, you get a number that you cannot write as a fraction. Okay? And you might say, well, maybe someday could we write it as a fraction? Like if computers get faster and we get more technology? No. You can actually prove to somebody that you can never write the square root of 2 as a fraction. So that's kind of a weird idea, to have a number that you can never write as a fraction, no matter how hard you try. Right? There's millions and millions of fractions. You can make up tons of fractions. But no matter what you try to make up as a fraction, you'll never get one that equals that number. It's kind of weird. With all the fractions out there, you'll never find one. It's impossible. All right. And then you take all the numbers that you can write as fractions, all the numbers that you can't, and that makes up the real number system. In Algebra 1, that's all the numbers that you study. If you're wondering, well, where do complex numbers fit in? Well, those would kind of be off to the side, right? Imaginary and complex. We're not going to look at those right now. So when you have this chart, one thing you can look at, kind of think of these as places, okay? And that'll help you with what I'm trying to point out. Think of this as like the smallest place, and then places that are getting bigger. So think of counting numbers as like Boston. Think of whole numbers as Massachusetts. Integers could be the Northeast. Rational numbers could be the United States. Right? And then irrational numbers could be another country, like France. And then real numbers could be Earth. So if you're in Massachusetts, are you automatically in the Northeast? What do you think? Yeah, if you're in Massachusetts, you're automatically in the Northeast. If you're in the Northeast, are you automatically in Massachusetts? It doesn't work that way. That's how this diagram works. If you're a whole number, you're automatically an integer, because you're also in the integer box. But if you're an integer, you're not automatically in the whole number box. Right? So if you're a counting number, you're automatically rational. Counting numbers are in the rational box, but not the other way around. Any questions on that? All right, so So we might take a look at that chart again when we do imaginaries, and we'll add to it. So some of these number sets have abbreviations, okay, single letters. These are all in your book. They're kind of weird, so I just drew them the best that I can. But I think the bottom one makes the most sense. It's kind of this capital R with this extra line. And that symbol is for real numbers. It kind of makes sense to me, R for real. The rational uses a Q, but it's got that extra line there. That's the symbol that means rational numbers. Why do you think Q? Anybody think of a word that begins with Q that has something to do with fractions? Zach?
Quotient.
Quotient, exactly. When you divide two numbers, it's called quotient. Maybe that's where the Q comes from. The Z for integers. Not sure. But that's the symbol they use. So where you might see that is you might see a homework question that says, write down all answers in the set, and maybe they'll do that symbol. If you see directions like that, write all answers in the set, and it's a Q. It just means only write down the answers that are fractions. Okay? If there's an answer that's not a fraction, for whatever reason, they don't want to know. Okay? You might also see a symbol like this. What do you think that would be? You know what the R means? It's got a little plus sign, so it's pretty much what you would think. Yeah?
Oh, the positive numbers?
Yeah, positive. What kind of numbers?
Rationals or real?
Real. So that symbol means positive real number. You could also do something like this, and it means just give me the negative real numbers for whatever you're doing. Okay? So you might see a little plus or minus. All right. So there are 4 basic binary operations in math. Binary means in order to do it, you need 2 things. And those are add, subtract, multiply, and divide. Can anybody think of an operation in math where you only need 1 number to do it? Like you could say, here's your number, do this to it. You only need 1 number. But if you said, like, here's your number, 5, I want you to add to it. Well, you got to tell me what to add in order to do the problem. So addition, you need 2 things, but some operations you don't.
Square root.
Yeah, if you said, here's your number, 6, take the square root. I can do it. I don't need a second number. Right, so square root. Has anybody seen this one before? Like a number with an exclamation point? That's factorial. It means 5 times 4 times 3 times 2 times 1. But you only need 1 number to do it. 5. All right, so we're going to look at a few properties, okay, some names of properties. What I'm going to do is I'm going to show you guys the property and see if you can tell me the name. So the properties I'm going to do on the right-hand side that you can see. And on the left, there's a name for that property. When I use the letters A, B, and C, A, B, and C could be any positive, negative, fraction, or decimal, or zero. Okay, it could be any number, any real number. And the first property is called closure. Okay, and I kind of asked you guys about this when I showed you the number set. I said to you, can you think of a whole number minus a whole number, and the answer is not a whole number. Okay? The idea of closure is that you start with a certain type of number, you do an operation like add, subtract, multiply, or divide with the same type of number, and the answer you get either is the same type of number or isn't. So let's say you take a whole number and you add another whole number. Will your answer always be a whole number? If you do a whole number plus a whole number, will you always get a whole number? Yes. So that means addition with whole numbers is closed. It means if you add a whole number to a whole number, you get a whole number. How about subtraction? If you do a whole number minus a whole number, will you always get a whole number? No. You could get a negative, which is not a whole number. That means subtraction is not closed. Okay? Closed just means that whatever type of number you started with is the type of number you end up with. Okay? Real numbers are closed under every property. If you add two real numbers, you always get a real number. If you subtract, you get a real number. Divide two real numbers, you get a real number. Okay? So closure is just that idea that whatever you start with, after you do the operation, you end up with the same type of number. Okay? That's called closure. How about this property? It says that basically it's saying that the order you add two things in doesn't matter. A plus B is the same as B plus A. Do you remember what the name of that property is? Yeah?
Reflex.
We're going to mention that one later on. Not yet, but that is going to be one we mention later on. Yeah? Commutative, right? Commute means to go back and forth, right? Like if I commute to work, it means I went from my house to work. I went from one place to the other. The A and the B went from one place to the other. They switched places. The second one I kind of already showed you. In the second one, there's no change in the order. ABC, ABC. It's exactly the same order. What is changed is the grouping. Okay? Think of associate. When you associate with people, you do it with others, you group, right? It's a group of people you associate with. So, on the left side, B and C are grouped. On the right side, A and B. And you could try it. Let A be 1, let B equal 2, and let C equal 3. If you add 2 plus 3 first and then add 1, it's the same as adding 1 plus 2 and then adding 3. You're going to get the same thing. Okay, this property, it says A plus 0 equals A. Basically, we say it's the operation that you can do, or it's the number you can use with addition that doesn't change it. You even know the name of that property. Okay, a hint is when you think of who you are, that's your what? How you would define who you are. It's your identity, right? It's the identity property. And the identity property kind of makes sense here because if you add 0 to something, you get back exactly the same thing. You get back what you started with. It doesn't change it, right? And that's like think of your identity. Who you are is who you are. It doesn't change on a daily basis, right? Adding 0 doesn't change it. This one's a little tricky, but I'll give you a hint. A and negative A. One word for those is opposites. There's another word that begins with an I. They are, yeah?
Inverse.
Inverse. So that's the inverse property of addition. These are all of addition. I could put commutative property of addition, associative of addition, identity of addition. I'm just not putting of addition on all of them. Inverse is the idea of opposite. You add something to a number to get 0. Okay? What do you add? You add the inverse, or the opposite. How about this property with A and then B and C? Sometimes you might even see that. A lot of people do that to visualize it.
Distributive property.
Yep, that's the distributive property. Now, I'm not going to write them all again, but you could write most of these properties not distributive. Distributive is only with addition or subtraction. Could have B minus C. But they have all the same properties for multiplication. Those are on page 2. So what would multiplication look like? Let me just pick one. Commutative. A times B equals B times A. 2 times 5 is the same as 5 times 2. That's the commutative property of multiplication. All right, so just some names of different properties. Any questions on those? We're going to do an example. I'll show you how you do a problem with these. a couple minutes. Okay, what makes something an equation? Like this, that's an expression, 3x plus 2. It's not an equation. An equation is something you can solve. You can't solve that. It's missing something to solve it. Yeah, Chris?
Never mind.
You want to take, yeah, Jared?
An equal sign?
An equal sign. So an equation is a statement of equality. What's the equality symbol called in math? An equal sign. So here's 3 examples of equations. These are all equations. 2x equals 12. 3 plus 4 equals 2 plus 5. And 5 equals 2. There are 3 different kinds of equations, though. They all have different names. Does anybody have any thoughts about any of those 3 equations? Any comment about any of them? Yeah?
One of them is an equal, the 5 equals 2.
Okay, can you say what about that one?
It's unequal.
Yeah, it's not equal. That's a contradiction. A contradiction is an equation that is false. We never said that equations always have to be true. You can have false equations. So this is called a contradiction. All right? So contradiction. How about one of these other 2 equations? Any thoughts on either one of those? Well, look at the 3 plus 4 equals 2 plus 5. Elias, what do you notice about that?
They both equal 7.
They both equal 7. So it's kind of the opposite of this equation. Instead of having 2 numbers that are different, you have 2 numbers that are the same. That equation is called an identity. An identity is an equation that's always true. You might be looking at it and say, well, yeah, it's just 7 equals 7. Obviously, it's true. But where you might see something like that is in Algebra 1, you could have a problem like this. And we'll have 2x plus, let's go like this, x plus 3 plus x. And I might give a problem like that in Algebra 1. Let's add a little bit more to it and say solve. Well, if you go to solve that, you're going to get 2x plus 6 on the left. And you're going to get, when you combine like terms, 2x plus 6 on the right. That's an identity. This is an equation that is true all of the time. You could pick anything you want for x. Right? So that's an identity. How about this equation? 2x equals 12. Is it always true? Is it always false? What do you think, Zach?
It's only true if x equals 6.
Yeah. There's a condition that makes it true. And that's called a conditional equation. It could be true if you pick the right letter. Okay. So we got equations that are always true, never true, sometimes true. Okay, but those are all equations. So equations have equal signs. Now we're going to look at 3 properties involving equations, kind of like associative, distributive, but these are specifically for equations. And when somebody already said one of them. So let me scroll down a little. Actually, you know what? Actually, no, I'm going to hold off on those for now. But somebody earlier said reflexive. That's a property that has to do with equations. Usually reflexive, symmetric, and transitive are 3 properties you study with equations. I'm going to skip over for now. All right, so let's look at this. And this is going to involve the names of the properties we just learned. So it says if x is any real number, show that what's on the left is equal to what's on the right. So there's 2 ways you could do this. I can give you all the steps on the right, and you tell me the names of the properties I'm using on the left. Or I can give you the names of the properties, and you show me how to do the algebra. Let's do it where I show you how to do the algebra. Okay. So I'm going to do this first. And now I want you to tell me the name of the property that I just used. Yeah, let's see, is it Emily? Yeah. Yeah, that's the distributive property. Okay, now I'm going to do this. 2x plus 6 equals 6 plus 2x. That property doesn't really have a name. All I did was simplify 2 times 3 and get 6. So, and I left everything else the same. So we could just call that we simplified. Now what's on the left and what's on the right are almost the same, but not quite. The last step would be to switch the order. And what property allows me to change the order of two things? Zach?
Commutative.
Commutative. So that's the commutative property. If you want to be specific, you could say commutative property of addition. That's not the commutative property of multiplication. It's addition. Any questions on that? Right. So on a test, you could see it either way. Maybe I would give you the property names, and you tell me the steps, or I give you the steps, and you give me the property names. Okay. What you're not going to see on a test is like distributive property, and then a line asking you to write the definition of it. You're going to see like how do you actually use it in a problem. Okay, so now we're going to get into coordinate system and graphing. So kind of a separate than property names. So we're going to start out with very basic, one single number line, not even a 2 number lines yet. When you have a number line, 0 is an important spot. What do you usually call that when you're graphing the 0 point, whether it's a 2-dimensional or 1-dimensional axis?
The origin?
Origin. And from the origin, positive numbers go which way? To the right or to the left?
The right.
To the right. So there's basic number line. Why do positive numbers go to the right? Because that's just what we do. It's what we decided on. Just like when you go up and down, whatever reason, positive is up, negative is down. So, once you put numbers on a number line, you no longer just have numbers that are arbitrary. You've kind of ranked them. You're saying that this guy is worth more than that guy. You've given them like almost like a ranking, right? And we can compare numbers now. And there's 4 symbols that we can use when we compare numbers. And the name of these symbols begins with an I. Anybody know what symbols I'm thinking of? Yeah.
Inequality.
Yep, inequality symbols. Okay, and the 4, well, let's see if you guys can tell me all these. The top one I just showed you, that was a less than. How about the one below it? Yep.
Less than or equal to.
Less than or equal to. The third one? Yep. Chris?
Greater than?
Greater than. And the fourth one? Yeah.
Greater than or equal to.
Greater than or equal to. So putting numbers on a number line allows you to use these symbols because you've now ranked the numbers. This one is bigger than this one. This one is smaller than that one. Things like that. Okay. Any question on the 4 inequality symbols? All right. So next thing we're going to look at is graphing on a number line. So that's with like the open circle, closed circle. We'll just go through that real quick. Does anybody know when you use an open circle, when you use a closed circle when you're graphing on a number line? Yep, Jared?
I think open when it is equal to.
Okay. So open when it's equal to, you think? All right, anyone agree or disagree? So You said use an open circle when it has the line, like the little line under it? So I'd use an open circle with one like that?
Yes.
Alright. Well, the way I remember it is you've got two types of circles, right? Open and then filled in. If you have a symbol that has the extra line under it, you have to take the extra step and fill in the circle. Okay. If you've got a symbol that doesn't have the extra line under it, then all you have to do is draw the circle. You don't have to do the extra step. Okay, so when you're graphing on a number line, you've got to make sure we use one of those two symbols. And there's actually another way to do it. Our book does it differently. Okay, I'm going to show you this way first because you probably did this back in Algebra 1. Then I'll show you how our book does it. It's not really hard at all. Okay, so in Algebra 1, I'd put down all kinds of detailed directions about this. But remember, the idea is put an open or a closed circle on your number, and then you draw an arrow shading in the direction you have to go. Or if you had two circles, maybe if it was like x is greater than 3 and smaller than 10, you'd shade between 3 and 10. Wouldn't be an arrow. Okay, so let's try this one. X is greater than or equal to 2. Alright, so if we're going to graph that on a number line, first thing we need is we need a number line. You can do it however you want. I mean, I think it's pretty simple just to go 0, 1, 2, 3. And you could put 0 in the middle, and some people put like 2 and -2 on each side. That works. All right, so first thing I got to decide is the circle. Is it Brianna? Okay, Brianna, what kind of circle would I need on 2? Open or closed? Closed. We've got the extra line underneath. Take the extra step, fill in the circle. Now we want to shade all numbers that are greater than or equal to 2. So which way am I going to shade? Well, Brennan?
I'm sorry, can you repeat the question?
Which way do I have to shade?
Which way do you have to shade? It's greater than 2. So you have to shade to the right.
Yep. All the numbers that are greater than 2 are going to go this way. Some teachers might have you shade above the line. I don't care if you shade above the line, on the line. That's fine. Okay. Questions on that? All right. Let's take a look at this one. 3 is greater than 5. Now, be a little careful with this one. What's different about the way that this problem is set up compared to the one up above? It's not set up the same way.
The variable is second.
Yeah, the variable comes on the right side. How can I rewrite this so the variable is on the left? Zach?
Y is less than 3.
Yeah, we can write it like that. That's the same thing. Anyone know why I would prefer that over the first way? It has to do with helping me to draw the graph. Why do you think I prefer y is less than 3 compared to 3 is greater than y? They're the same thing. Yeah, Emily?
Now you're saying y is like the beginning, so it's your starting point, so you can visualize how you want to draw it.
Okay, can you explain more how this helps me to visualize which way to draw it versus this one really doesn't? Why does this one help me visualize which way to draw it better?
You're starting with y, I guess. I don't know.
So you're on the right track, but anyone think they can tell me why this one helps you visualize the final answer better than that one? Yeah. Yeah. So, yeah, it's all about this. Yeah. Right? If you put the variable on the left, this tells you which way to shade. If you put the variable on the right, it doesn't. This tells you the opposite of the way to shade. So I always put the variable on the left, and then I always know which way to shade. Look at the direction it's pointing. All right. So, got our number line. How about, Eric, what kind of circle do I need this time?
Open.
Open on what number?
3.
Yep, open on 3. And Jacob, I'm going to shade to the...
What?
Yep, I'm going to shade to the left. That's it. Any questions on graphing? Okay. So, same two problems again. In our book, they use a bracket instead of a closed circle. It's just a different symbol. Everything else is the same. So if you wanted to graph this one using the symbol in the book, they use a bracket. So instead of a closed circle on 2, you put a bracket on 2. It's important, you have to think about which way the bracket faces. With a closed circle, you don't really have to do that. But the bracket is going to face the direction you're going to shade. So this is how you would do this one. Using the symbol in our book, bracket. Now, the book uses a bracket for a closed circle. Any guess on what symbol they would use for an open circle? It's going to be kind of similar to that, but yep. They use a parenthesis. Think of a bracket, like a bracket closes things in more. That's how I think of it. Where a parenthesis is more open, the bracket is closed in a little more. It's got 3 sides on it. Closes it in. All right, so bracket, closed circle, parenthesis for open. So same idea. Put your symbol on the 3. Just remember which way you're going to shade. Shading left. If this was a question on a test, I don't care which way you do it, whether you use open circles, closed circles, brackets, or parentheses. It's just maybe I would give you a multiple choice question like this and say, here's a picture on a number line. Tell me what inequality this would represent. And you'd have to write y is less than 3. So you'd have to know this symbol means less than. Any questions on that? All right, let's look at this one. So this is kind of a special inequality where you have a variable in the middle and you have a number on each side. This is a conjunction. It means and. And if it confuses you to think of it all together, you can kind of think of, there's one part, 2 is less than or equal to x, and there's the other part, x is less than or equal to 9. It's just like writing that. 2 is less than or equal to x, that's what I put right here, except I wrote it with the variable on the left. So x is greater than or equal to 2, and x is less than or equal to 9. So if I were to graph this one, what kind of circle would I put on the 2 and the 9? On both. Yep.
Closed circle.
Closed circle. Or, Kaya, what kind of bracket could I use? Kaya, oh, you moved in there. Okay, that's fine. If I didn't want to use a circle, I could use a closed circle. I could use a parenthesis would be for open.
So the bracket.
Bracket. Yep. So you could do bracket or closed circle. Just don't mix them. Pick one or the other. Okay. So let's set up our number line. 0, 2, 4, 6, 8, 10. I'm going to do closed circle on 2, closed circle on 9, And where would I shade? Yeah. So like this way?
Yeah.
Like that? So let's pick a number over here, -5. Is -5 greater than or equal to 2?
That's greater.
So shade to the right?
Now think about the top part.
So like right here?
Yeah.
All right. Let's pick a number here, like 20, way down there. Is 20 greater than or equal to 2? Yeah. Is 20 less than or equal to 9? No.
Yeah,
No, 20 is not smaller than 9. So it's not really left or right. Where would we shade here? In the middle. Yeah, whenever you have a conjunction, it's the only time you don't draw an arrow. You just end up shading between. Okay? Any questions on that? It's one kind of one-dimensional graphing on a number line. Okay. Absolute value. So, very simple. Absolute value is, if you want to think of it in terms of geometry, it's a distance from the number 0. Distance. If I give you a distance between any 2 points in the world, I have to give you a number that's what? Yep.
Positive.
Positive. Okay. And that's the idea of absolute value. It is always positive. So we'll just do a real couple quick examples. Absolute value of 6. How about is it Nakeda? Nakeda? Okay. How would you say, what's the absolute value of 6? 6. And how about absolute value of -3? Well, Elias. What's the absolute value of -3? 3. Okay. Any question on that? All right. So, last thing we can really do with a number line with absolute value is figure out how far apart 2 points are. What operation would you use in math? If you had a point here and another one here, you want to figure out how far apart they are. Oh, Sam? Well, let's say like we got a point here we'll call A, and a point here we'll call B. And I want to know how far apart it is from A to B. What could you do with A and B to figure that out?
Subtract.
Yeah, subtract them. Like if this was 2 and this was 15 and you want to know how far apart they are, 15 minus 2, 13. Or you could do 2 minus 15. Doesn't matter which way you do it if you take the absolute value. Okay, so distance between 2 points is the difference of the absolute value. Right, so let's set this up. Find the distance between -2 and -9. What I just wrote there, that's from the formula. Jacob, what would be the first thing I would subtract?
-9.
Okay. And the second thing?
-2.
-2. It's important he said -2. So now we got -9 minus 2. What's going to happen there? -9 minus 2. Yeah. Chris?
The negative -2 will become positive.
Yeah, it's going to become -9 plus 2. And what's the absolute value of -9 plus 2? 7. So a simple example of how you just find distance between 2 points on a number line. All right, so now let's look at 2D. Someone tell me anything they know about two-dimensional graphing. What's something that you know? Yeah?
It's X and Y.
What's x and y?
I don't know, plane? Oh,
Okay, so together the x and y axis make up a coordinate plane.
yeah.
Yep. Go ahead, Zach.
Y equals M plus B.
Okay, so that's if you want to graph a line, that's this slope-intercept form of a line. What else about graphing in 2D? Even more basic stuff, just about the plane itself. Yep.
There's 4 different quadrants.
Yep, there's 4 different quadrants. How about where the 2 axes cross each other? What's that called? Yep.
The origin.
Origin. Positive numbers go which way on a 2D system? Emma?
Right.
To the right and up. And how about negative numbers? Yeah, down and left. I think that's pretty much everything. So 2D, you guys mentioned quadrants. They're just numbered starting in the upper right, going counterclockwise. 1, 2, 3, 4. I don't know if we said it specifically. We said there's 2 axes. The x is the horizontal, y is the vertical. Positive is up and right. Negatives are down and left. How about that I just put on the board? What do you call that? Besides a dot, something a little more specific. Yep.
Point.
A point. Yep. What else is it called? A coordinate. Yep. And specifically, this is a 2-dimensional coordinate, so we call it an ordered pair. You could also have a 3-dimensional coordinate. That's called an ordered triple. This is an ordered pair. Okay, so any questions before we do some stuff on the calculator? Just the basics about 2D coordinate systems. So we're doing a lot of different things. Once we get through chapter 1, we're going to pretty much focus on one thing per lesson. We're not going to jump from like covering properties to graphing with closed circles to then talking about coordinate planes. It'll be one thing. Okay, so zooming on a graphing calculator. So zooming basically changes how much you see on the screen. When they tell you to do this, there's 4 values they're telling me to type in. Those 2 values are for your x-axis. This is called your x-min. This is your x-max. They're always in this order. The next 2 values that they give you are for your y-axis. y-min, y-max. The hard part is not changing a window to some numbers that they give you. That's easy. The hard part is figuring out what these numbers should be on your own. How big, how small. That's the hard part. So, on your calculator, what we're going to do is we're going to set a window from -20 to 20 and -20 to 20. What I want to do, so everyone's kind of in the same spot, is start out by pressing, after you turn it on, press zoom, and we're going to go 6. Zoom 6. 6 says zoom standard. What zoom standard does is it sets your window from -10 to 10 on the x-axis and -10 to 10 on the y-axis. It's basically just it's a starting point. Now, if you see something on the screen, that's because somebody left something in there. Does anybody see something on the screen? Yeah, what do you see? Dots?
Oh, it's, yeah.
So if you see dots, what we're going to do is press y equals, and I guarantee you one of these 3 things is highlighted. Either plot 1, plot 2, plot 3. Am I right?
Yeah.
Probably looks like this.
Something like this.
Look like that? Alright, so now after pressing y equals, highlight that plot, and what we're going to do is press enter, and that turns it off. Yeah?
My plots weren't highlighted, but it showed like arcs.
So if you had a picture, you probably had something typed in there, maybe something like that. So that's just a line. But if you saw something on the screen, like a curve or something, you can just press the Y equals and then press clear. So between clearing the screen of those graphs and turning off the plot, you shouldn't have anything on your screen now. It should look just like that. Is there any ones that doesn't look like that? Yeah? Yeah, so you want to press the up arrow to highlight plot 1 and then hit enter. And that'll turn that off. Okay, does everybody's look like that? All right, now what they want us to do is set a window from -20 to 20 and -20 to 20. Okay, let me show you why you might have to do that. I'm going to type in under y equals x, which is right below mode, squared, which is over on the left-hand side, plus 10. And I'm going to hit graph. And if you type that in and you've done everything the way I've shown you, you see the little yellow circle in the upper right-hand corner. That means the calculator is doing something. And now mine just stopped. Well, where's the problem? That's what that shape is. It's a U shape. It's off the screen. It's actually up here. So how can I see it? Set my window a little bigger. So to type in these values, you're going to press window. There's some other stuff there. You don't have to worry about that. What we want to type in is -20 for the X-min, 20 for the X-max, -20 for the Y-min, and really, the only value you had to adjust to be able to see the graph that I just did was Y-max. You could have left all the other ones the same. But the problem wanted you to change all of them. So making Y-max 20 is what's going to zoom you higher. Now you can see the parabola. Right? So if you typed that in, your screen should now look like that. Yep.
Mine's not showing
The axes. So if your calculator is not showing the axes, you can press second format. And you can go to, let's see, axes, and make sure they're on black, because if the axes were white, you wouldn't see them. Are yours on black?
They were just set off.
They were set to off, okay. So, yeah, if you go to the axes, you can change the color. His were on off, so he had a screen that looked like that. Usually we want to keep the axes on. And I usually just keep them on black. Okay. So any questions on how you set a window? So in the homework, they may say, set your calculator to a window. There's nothing you have to write down for that problem. You just have to try it on the calculator and that's it. Okay, so you will get some homework questions that you could just write on calculator.
What buttons did you press to put the equation?
To put the equation, I went to y equals, and then I typed it in under y1. You can type in up to 10 equations at the same time. But yep, it's under y equals.
Why is there a box where the X was
A box where,
black box?
do you have like something like that, a little box like that with dotted lines? So if you've got something like that, just press clear. It wasn't that?
It was the black box with the two white windows.
The black box with the two white
That
windows.
was right after the equals.
So you press the X button, and then squared, and then I just typed in something like, I think I did plus 10. So I don't think you'll get that little cursor blinking, but you still have it on the screen. Oh, okay. Yep. All right, so last thing we'll look at, I think, yeah, last thing, is what's called the distance formula. Okay, how to find the distance between 2 points. So if we had 2 points, let me just kind of draw it. Call this point P, point Q. And I want to find the distance between them. The distance formula really is another formula you know from geometry. Can anybody think what shape I could turn that line segment into? I got to add a couple things to it, but I could make it into this shape. And then there's a theorem from geometry that if you know 2 sides of this shape, you can get the third. Yeah?
Triangle?
Yeah, we could make it into a triangle just by doing something like that. That's longer than I need, but that's fine. So put in a horizontal through P, and then put in a vertical through Q. So I just made a triangle. And now, does anybody know what theorem you can use from geometry? If you've got 2 sides, you can get the third side.
Pythagorean.
Yep, the Pythagorean theorem. So when you want to find the distance between points P and Q, what you really are doing is you're finding this distance in red, which, remember what we just talked about. How do you find the distance between 2 points on a number line? You use subtraction. x1 minus x2. That's x1. That's x2. So you subtract those 2 points, and it tells you the length of the red. Now for these, you're still going to use subtraction because you want to find the length of that segment in green, but it's vertical. What letters have to do with the vertical? We just did the horizontal.
Y.
Y. Right? y1 minus y2, that's your vertical. y2 is up here. y1 is down here. And once you find each of those lengths, this is just the Pythagorean theorem. Take the length of one side, square it. Take the length of the other side, square it. Add them up, and take the square root. So the distance formula is the Pythagorean theorem. Okay, so let's find the distance. Oops, make that a little bigger. Distance between these 2 points. 1, 4 and 5, 6. If you want, you can label each number before you plug them in. What would the number 1 be? Actually, I have 2 choices of what it could be. Yeah, Chris.
4?
What is it?
4?
The number 1?
Yeah.
What could it? So it's going to go in one of these 4 spots.
Oh, 1. Would be 1.
Which is? Can you just say the name of the spot so I know which one you mean?
X2.
It could be x2.
No, I'm done. No, right. No.
No, it could be x2.
X1 is 5, and X2 is 1.
So it could either one, right? You could make one x1 or x2. It doesn't matter.
Okay.
So which one do you want to make it?
X5. 5. 5.
So you want to make this one which spot?
Oh, X2.
X2. Okay.
Sorry.
Yep. Now that he decided that, now there's no other choices. The 4 has to be the y2. And the 5 and the 6 have to be the x1 and y1. x1, y1. Okay, let's find the distance. x1 minus x2. 5 minus 1. Square it. y1 minus y2. 6 minus 4. And square it. Okay, so if I do that, Elias, 5 minus 1 gives me 4, and then square it. 16. 6 minus 4 is 2. 2 squared is 4. 16 plus 4 is the square root of 20. And anytime we get a square root we can reduce, we need to make sure we reduce it. How do or what would the square root of 20 be if you reduce it? It'd be like 9 square roots of 50 or something. That's not the answer, but that's what I'm looking for.
2 times the square root of 5.
2 times the square root of 5. If you're not sure how Zach did that, one way to do it is like this. Factor the number 20 into 4 times 5. Okay. 20, square root of 20 is the square root of 4 times the square root of 5, and the square root of 4 is 2 square roots of 5. Okay. That's something more from like algebra, maybe algebra 1, algebra 2. But something we use right there. And that's how you find the distance between 2 points. Okay, so last formula, a little bit easier. It doesn't have squaring, square roots, anything like that. It's the midpoint formula. So distance formula tells you how long, or the distance between 2 points. Midpoint formula tells you where the middle is between 2 points. Now, you really don't even have to memorize this formula if you just kind of use common sense. If you add up 2 numbers and divide by 2, which is exactly what we're doing, add up 2 numbers and divide by 2. There's a name for that. Anyone remember what that's called? Add up 2 numbers and divide by 2?
The average.
The average, or the mean. So the midpoint formula basically just says average the x's and then average the y's. And that's it. That's how you find what's in the middle. Okay, so let's find the midpoint between those 2 coordinates. -5, 2 and 3, 7. Okay, what's the average of -5 and 3? So add them together and then divide by 2. There? Yep. -5 plus 3 over 2 gives me -1. Comma, and what's the average of 2 and 7? About Kate? Average of 2 and 7? Well, add them up. 9, and then divide it by 2. 4.5. Yep, 4.5. So you could change it to a decimal like she did, or you could just leave it as 9 halves. That's fine. Either way. So, just to show you what we did, 2 plus 7. That's how you find the midpoint. Any questions on that? All right, so a lot of different things there, but we got to end a little bit early. You've got just under 15 minutes, about 13 minutes or so. So that is the homework for tonight. Page 11, 5 through 16, 20 to 23, and then 28, 31, 32, and 44. Okay, so you got a little bit of time. If you'd like to start it, there are some books on the bookshelf. There's 4 of them stacked up, so you could share with someone next to you, or if you pick your book. Also, if you have any questions, like you tried to get the calculator working at home, couldn't quite figure it out, or anything about that, now's the perfect time to come talk to me.